One of the situations that we're going to deal with is we're going to have a long straight wire with a current running through it, and we're going to put that wire in a magnetic field, and we're going to get a force on it. Now, we're going to keep it really simple, just straight wire, magnetic field, force on it, and so on. But this is really super important because this is what allows us to create electrical motors. This is kind of the fundamental science of an electrical motor. Inside an electrical motor, you have wires with currents running through them, and they're in magnetic fields. And that allows forces to be applied in such a way that it will spin the motor. So obviously we're dealing with torque as well. But we'll get to torque next time. But this time we're just going to deal with the force on a length of wire in a magnetic field. So here's our wire. And let's say we've got a current flowing up the wire. So here's our current. Now remember that current is the flow of positive charge. Now what really flows in a wire? Electrons, which are negatively charged. So if I draw the current like this, what's really happening is electrons are moving down the wire slowly with some drift velocity. But in our imaginations, we imagine that it's the positive charge carriers going the opposite way. We have to. I mean, that's just convention, and we're never going to change it, so just deal with it. So that means you've got charged particles moving up here. And remember what this current was. This current, well, anyway, we'll get to that in a second. I'm going to put a magnetic field in here, like this. So here's the strength of our magnetic field, and we're going to call it B. Now, you know what, we're running low on time, so I'm just going to give you the simplified version of this. And we can go back and go through the nitty-gritty of it, you know, next time. But remember, we had an equation for the current in terms of the drift velocity, right? And the number, the charge on each charge carrier, the number of charge carriers per unit volume, the drift velocity, and the, what was it, I forget now, the area or something. We can do that in terms of each charge carrier. I mean, it really follows from this. F equals QV cross B. I mean, that's what we just talked about, okay? If we apply this equation here to each little charge carrier in there and then sum them all up, what we get is one of my favorite equations of the year. And I think you can turn this by using the idea of the current here. F equals, well, we're going to get a force on the wire. Now, let's think about why. Let's take a look at one of the charge carriers. You see it has a drift velocity up the wire. So if it has a drift velocity, there's going to be a little tiny force on the wire, or on the charged particle, and that's going to push the wire to the side. And you go V cross B. It's going to be a little tiny force to the left. Does everybody agree with that? Right? When you go V cross B, you get a little tiny force. So, but there's zillions of these, literally zillions, of little moving charged particles with this drift velocity in the wire. Well, when you add all those forces up, you get the total force on the wire. And, well, yeah, read page 901 if you want to get how to get from here to here. But I just want to kind of get to it. Now, this current represents the motion of all these charged particles in here. Now, there's also going to be a displacement. The currents are going to move from here, the charged particles are going to move from here up to here. And I'm going to call that L. And that's the displacement of the charged particles. And then it's going to depend on, and that makes sense, doesn't it? If I'm adding up all the little forces, the longer the wire that's in the magnetic field, the more force I'm going to get. And then the strength of the magnetic field. Now this L right here is a displacement. It is a vector. Current is not a vector. It kind of looks like it ought to be. There is a displacement of charged particles involved. But current is just a measure. If you draw a cross-sectional area and you count how many charges move through that cross-sectional area in a per unit time, how many coulombs of charge go by per second, that's a scalar quantity. There's really no direction associated. You're just counting how many charges go by per second. But the charges themselves do have velocities, and therefore that's a vector, and they have displacements. So we're going to call this L. This L has a direction. It's really kind of the direction of the current. All right, even though current doesn't have a direction, right? I don't know. It's confusing, but you go, okay, the current's moving this way, so I'm going to say the direction of L is up. Okay, crossed with the magnetic field. And here's my Paulson cloud. Now, why is this my favorite equation? This describes how much force is on the wire that's in a magnetic field, because it has current and length, and it's in a magnetic field. And the cross product gives me the direction of the force. Now, why is this one of my favorite equations? Well, when I first started teaching this class, back in 94, 95 school year, you guys were born that year. That really depresses me. Okay, they didn't give you an equation list to use on the AP test. We had to memorize them all. So we were coming up with ways of memorizing equations. And so we would give them names. And this, I can't remember who the student was, but one of the students came up with a name for this. Phil Crosby. Phil Crosby. So Phil Crosby will tell you what the force on a wire is that's in a magnetic field. Okay. And then that will be now if I have a magnetic field and I'm going to use this, let's just have I'm just going to draw a really big field here. What if I have a curving wire in here? Okay. Well, then what I'm going to do is I'm going to say, well, let's let B be a constant for right now, just to keep it easy. Doesn't have to be a constant. We'll make I a constant, and we're going to keep it. We're only going to deal with steady currents in this class, except for RC circuits and except for when we don't, we're going to use steady currents. Steady currents means the current doesn't change with time. It's constant current. Okay. Well, this right here is going to have a little force on it, and I go, here's the current, but if I look at my little charged particle, it's going to have a little tiny displacement. And let's call it, we could call it dl. I think the book calls it ds. They go from using L to ds. It's okay. So here's my little tiny displacement. I'll just use ds. And so what is the force on that? Well, the force, the little tiny bit of force, d force, hey, what's the force? All right, is equal to, well, Phil Crosby, but now it's doesn't spell Phil anymore. It's I times ds crossed with b. Okay. Now, to figure out the total force on this wire, if you start here and it's got current for it and maybe it ends here, you have to sum this all up. You have to integrate. And it's kind of a weird integral, isn't it? Oops, I forgot the vector hat there. Because here's the little, that little dx thing, or the little, I forget what you call it in calculus, your variable integration. It doesn't have to be at the end. In fact, we're going to keep it away from the end. Why? Because we need this cross product, and the order of the cross product matters. Well, so now, really, when I go ds cross b, especially if b is constant right here, when I look, notice that I and b are constants, right? I'm just taking the cross product of this. Well, what that's going to give me when I sum all the ds's, look at all the ds's. When I sum all the ds's, what do I get? I get delta s. I get the total displacement. Boom. Boom, winning. This is my total. This is delta S, or you can think of it as being L. So we're just going to use that. Okay. Now, here's a little law. What if I go in a loop? Okay, and I'm running out of time here, so I'm just going to go in a loop here. I'm going to start here. Let's say my wire goes in a complete loop. Like that.
Is that called where it doesn't matter how you get there?
Conservative force.
Yeah. Well, magnetic force is not a conservative force, and we'll talk about why that is later. But anyway, look, if I add up all the little forces acting on here, well, B is a constant, I is a constant, but what's my displacement if I go from here to here? It's zero. Yeah, very good. So I can say that the force, if I go I, and then I'm going to go ds cross b. What does this mean, this little circle right here? It's a closed, well, if I'm doing a surface integral, it means a closed surface. But this is a line integral, so it means a closed loop. No, that was a very good guess. It means that I'm anywhere. I'm going in a closed loop here, like that. It's going to be equal to 0. Okay. And so the force will be 0. Now that's the net force on the total loop will be 0. Now that doesn't mean the torque will be 0. We're going to talk about that next time. But anyway, here it all comes down to this. This is the force. If you have a particle. Hey, last thing. I got 30 seconds. I'm going to use them. If you have a particle moving in a magnetic field all by itself, use this one. If you have a current in a wire running through a magnetic field, use this one. Okay? It will describe the force you get when you move charge through a magnetic field. That is all.